Redshift modeling results. Our analysis suggests that the Millar Cosmological Model, or MCM, which introduces a friction-based redshift amplification mechanism called frictomass, provides a compelling extension to the standard cosmological redshift framework. While the standard model, using Hubble's law alone, adequately describes low to intermediate redshift observations, it increasingly underestimates the observed redshifts of distant Type 1a supernova, an inconsistency traditionally explained by proposing dark energy. By incorporating a linear friction coefficient, the MCM improves alignment with observed data, producing higher predicted redshifts over cosmic distances without requiring exotic forces or changes to established physics. Further refinement using a bell curve friction profile, which represents a peak resistance mid-journey that diminishes near the source and the observer, produces an even closer match to the observed acceleration pattern, again without needing dark energy. These findings suggest that the universe's large-scale redshift structure may result from a combination of cosmic expansion and photon interaction with the memory fabric of space itself, offering a testable, physically grounded alternative to the dark energy paradigm. Methods. To evaluate the predictive strength of the MCM compared to the standard model, we performed side-by-side numerical modeling using publicly available Type 1a supernova data as a baseline. First, we calculated the standard redshift distance relationship using Hubble's law, z equals h at d or c, where z is redshift, h is the Hubble constant, 70 kilometers per second per megaparsec, d is distance in megaparsecs, and c is the speed of light in kilometers per second. We then extended this model by applying two additional friction-based calculations proposed by the MCM. The first was a linear friction model, constant friction coefficient multiplied by distance. The second used a bell curve friction profile, modeling peak resistance in the middle of the photon's journey, tapering off near the start and end points. Redshifts were calculated for distances ranging from 100 to over 9,000 megaparsecs. These were compared across three models: standard, linear friction, and bell curve friction, and evaluated against the supernova redshift range reported by the Dark Energy Survey, extending up to redshift 1.13. Discussion. The results demonstrate that the Millar cosmological model introduces a new, meaningful physical mechanism, memory fabric friction, that brings theoretical predictions into closer alignment with observed redshift data at cosmic distances. While the standard model adequately describes redshift at lower scales, it fails to account for the increasing acceleration seen in distant supernova observations without introducing dark energy. The linear friction model raises the predicted redshift values in a manner that aligns with these observations, providing a natural explanation based on the interaction between photons and the stretched memory fabric of the universe. The bell curve friction model offers an even better fit. It captures the rise, peak, and eventual leveling off of redshift amplification, matching the pattern seen in large-scale cosmic surveys. This suggests that photons traveling through the universe are not simply stretched by expansion, but also experience tension that builds up and relaxes depending on the cosmic landscape they traverse, denser in the middle, calmer near the source and destination. Importantly, this explanation requires no new energy field or violation of known physics. Instead, it reframes redshift as the sum of two effects, expansion and friction. This opens new observational pathways, such as examining light passing through dense galaxy clusters versus cosmic voids, to test the model's predictions. Conclusion. This study proposes a new interpretation of cosmic redshift through the lens of the Millar cosmological model. By adding memory fabric friction as a contributing factor, the model explains the observed acceleration of redshift without the need for dark energy. The bell curve friction profile, in particular, matches observational data remarkably well, suggesting that the structure of the universe itself, not some mysterious force, shapes the redshift signature we observe. This challenges the dark energy paradigm and offers a fresh, physically grounded way to understand the structure and evolution of the cosmos. We invite the scientific community to consider this model's testable predictions and explore further data comparisons, especially in regions of varying cosmic density, to validate or refine these findings.